Okay, let's go ahead and work this example now of work. And in this example, we have a shopping cart that's being pushed along, and it gets pushed for 20 meters. And we're told there's a force of friction that's resisting its motion that is this way with a force of 35 newtons. Okay? And in the first part of the question, we're asked to calculate the work done by friction. Okay? So work done, remember, is the force times the displacement times the cosine of the angle between the force and the displacement. So we'll need to apply that here. So in part A, work done by friction, well, the force of friction is 35 newtons. Okay? Displacement is 20 meters. Now we have to do the cosine of the angle between the force and the displacement. So force is to the left, displacement is to the right. So that means that's a 180-degree angle between those two. The cosine of 180, that's -1. Okay? So 35 times 20 times -1 gives us a value of -700 joules for the work done by friction. Okay? So negative work, remember, means energy is being taken away from our system. Energy is being taken away from our shopping cart. Now, part B asks to calculate the work done by gravity. So gravity, remember, pulls straight down with a force of mg. Okay? Now, work done, remember, is proportional to the cosine of theta. Okay? So what's the angle here between gravity and displacement? Well, displacement, remember, is to the right. Gravity is straight down. So that's a 90-degree angle between those two things. And the cosine of 90, which we need to calculate the work, the cosine of a 90-degree angle is 0. Okay? So the work done by gravity is 0. Okay? Now, we could do the same thing for the normal force acting on the cart. Okay? So gravity pushes down, the floor pushes back up on the cart with the normal force. Now, since the normal force is also perpendicular to displacement, that's a 90-degree angle, we have cosine of 90, that's 0. So this is also the work done by the normal force. Okay? So those do no work. Okay, now the last part of the question, we want to know the work done by the shopper's push. Okay? Now, we're not given that, the force of the shopper's push in this question, but we can easily figure it out. So the cart is moving with constant velocity to the right. So the acceleration of the cart is 0. If the acceleration of the cart is 0, that means the shopper's push is just matching the friction force. So therefore, our shopper here is pushing to the right with a force of 35 newtons, exactly equal to the friction force. Okay? Okay, so now if we want to actually calculate the work in that situation, let's slide this over a bit here. Okay? The work is force times displacement times the cosine of the angle. So the work done by the shopper's force, okay, is 35 newtons, that's the force. The displacement is 20 meters. And it's times the cosine of the angle between the force and the displacement. Now, if the force is to the right, displacement is also to the right, that means our angle is 0. and the cosine of 0 is 1. So therefore, the work done by the shopper's force is 35 times 20 times 1. That is plus 700 joules. Okay? So the shopper is doing positive work on the cart. The shopper is adding energy to the cart. But that energy is being taken away as fast as the shopper is adding this energy to the cart, friction is taking it away. So that the total work done is 0. 700 minus 700 is 0. Gravity and the normal force do no work. That's 0. So the total work done on the cart then is 0. So there is no actual energy being added to the cart then. I mean, we know that's the case because the cart is still moving with the same velocity the whole time. So a total work of 0 means there is no net energy input to the cart.